So I'm here today to talk about some of the practical considerations of microservices, or really any fine-grained architecture. I've done a couple of talks recently talking about some of the more generic concepts behind it, and really I wanted to talk more about some of the practical details that you're going to have to consider if you want to look at microservices or fine-grained architectures in your own organizations. As was mentioned, I work at ThoughtWorks. We're a software consultancy. We build software for a living. We are hiring. We are always hiring. We have a booth. We have 4 offices in Australia. We're even in Perth, to give you an idea of how broad our range goes. So I'm Sam. I've been with ThoughtWorks for 10 years. You can call me Sam or Samuel. King of the North also works. I would rather Jon Snow references, but I'm apparently, you know, although I look a bit like one of the missing Stark children. Anyway, I think what we've had over the last sort of 10, 15 years is a whole load of theory and practice that's come out of various different places, experiences from the enterprise world, or experiences that have been captured in books, or theses, or terms like guerrilla SOA, or rest in practice, and all this sort of stuff, which has all helped us understand how we move from the big monolithic systems of the past to more fine-grained architectures and more fine-grained systems. These are things and information as diverse as things captured in Eric Evans' domain-driven design book, which gives us clues as to how to factor our services to ensure that they're loosely coupled and highly cohesive, or things like Alistair Coburn's sort of ports and adapters or hexagonal architectures paper, which talks about what are the characteristics of a well-factored service and trying to avoid some of the perils of the overly layered systems of the past. So we move away from these big monoliths where everything's in one giant box, or even these horribly layered systems that are often beloved by vendors. I remember seeing many papers about architecture from Sun, for example, that would have a 3-tier architecture, and the middle layer would be business logic. And I always thought, well, if that's the business logic, what the hell are we doing in the other boxes? I often call these onion architectures, lots and lots of layers, and when you cut through them, you want to cry. So instead, with sort of hexagonal architecture, this idea Alistair talked about, we think about these well-factored services where really no one service is more important than the other. They're more peers of each other, and they sort of fit together nicely. And we're talking to them over sort of well-defined APIs. And if you think about the concepts from domain-driven design, these microservices should be factored really around bounded context, the idea of having groups of like-minded functionality modeled around your business domain, sort of in one service boundary. This actually helps us ensure that we actually have very good, well-defined interfaces between them, like we do, say, between functions within an organization. This helps us avoid some of the problems where business logic can be smeared all over a multi-layered architecture. These finer-grained services actually can be netted inside each other. So if I have a service boundary, which I'm talking to over HTTP, and I want to more finely break up that service, so maybe I go from having a customer-bounded context and subdivide that into, say, registration and management, I can do so behind that boundary without the outside world having to know. And these sorts of techniques allow us to build things where the services can often be significantly fewer than 1,000 lines of code, and certainly in some organizations I've spoken to and some of our clients, these services are often under a couple of hundred lines long. These are services that can be written in a day or a week, not months or years. Finer-grained architectures actually allow us to think about different ways where we can align our architecture with our organizational structures. Those of you who know Conway's Law know how important that can be to actually make sure that the architecture isn't at odds with how our organization communicates internally. And now I can actually look for seams in a monolithic system and break up a more fine-grained architecture, maybe along geographical or organizational divides. Also, when thinking about wanting to change our software, in the past with the big monolith, and I want to change a single line of code, I have to redeploy the monolith. Now, if that line of code is a change in one service and one service only, I can deploy that one change by itself, allowing me to actually deploy my software more frequently. This is actually often one of the main drivers of people moving towards more fine-grained architectures, is a desire to put functionality out much more quickly. Even better, I can experiment with new technology. When I have a big stack and everything I've got is in my large monolithic application, and I want to say try a new language or a new web framework or new persistence layer, that's always a high-risk maneuver when I've got my entire stack. You'll often find that organizationally there's a lot of impediment to bringing in new technologies in that sort of world because everybody's worried about what might happen. And yet if my system is subdivided into smaller units, I can maybe take a small component in that, maybe the least risky part of it, change the technology there, learn about it, and then potentially apply that change elsewhere within my organization. So people who use these finer grained architectures are often much more able to take advantage of new technology as it comes out to help them maybe take advantage of being more productive or being happier, more well-rounded individuals. Now the concern that some people have around the fine-grained architectures is that of performance. Okay, we used to do one database call for this operation, now we're doing 15, and there's lots of communication across the wire. In reality, when you move towards more finer-grained architectures, you often find yourself with many more options about how to scale your application to handle different load. Whereas before I'd have to scale the entire big box and put it on a bigger box, I can now take those independent components and actually fine-tune those individual units to make them do what I need them to do to achieve what my customers do. So these fine-grained components offer us a whole load of benefits, moving away from the big monolithic applications of the past into towards the more fine-grained sort of applications of today. The problem is a lot of this complexity that goes out of the monolith, this sort of accidental complexity we often call it, becomes complexity in the system itself. It often becomes much more evident, but it's still very much there. And for those of you in sort of slightly larger organizations, maybe with teams of more than 10 people or so that are involved in working on these systems as a whole, one of the main challenges you're going to have to face is where do I standardize with this system and where do I actually move towards giving people the ability to do whatever they want to do. A lot of the reason that people move towards finer grained architectures is actually to allow them to respond and react more quickly. If you think about the world of standardization, this gives a lot of consistency. So do I need to standardize in terms of my languages, my technology stacks, because it's one big monolith? Well, I probably do need to be using the same tech stack there. Consistency also gives you safety. Does this stuff work? Well, we've used it everywhere else, so of course it works. Within the free-for-all, you get a sense of autonomy. I'm empowered to do what I need to do a good job. And it also gives me ability to react. I've got a problem right in front of me. I'm not beholden to some service manual that says exactly what I should do. I can pick the right technique, the right tool for the job to do what I need to do. People who want to move towards more fine-grained architectures are often looking towards more towards the sort of reaction, being a bit more autonomous in how they do things. They want to get things out faster. They want to be more reactive. But there's still a need to standardize. So where are you on that spectrum? Jim Highsmith actually talks about his concepts a lot in his thoughts behind actually adaptive leadership. He talks about this sort of spectrum between responsiveness and responsive executives and people that really, they focus and prioritize towards being incredibly reactive to maybe market conditions or a new business requirement that comes down the line, as opposed to those organizations that optimize for efficiency. And ultimately, you can't have both things at once within the same area. You can't at the same time be incredibly efficient by standardizing the tech stack and at the same time give people complete choice over the right tech stack to use to be as responsive as they can be. So you often have to make a choice. He actually refers to it as a paradox, effectively. You can't have both these things, and unfortunately you can't resolve a paradox. My CEO, Go Shao, actually says, a paradox doesn't have a solution, it has a resolution. You effectively pick what makes sense for you right now. And that's probably what you need to think about as you move towards finer grained architectures. Where is the point on that line between standardization and sort of letting people have as much autonomy as they can? Where do you need to pick that line? And most of this talk is actually about those areas where you probably do need to standardize for your own sanity based on the experiences that I've had and many of my colleagues and friends in the industry. So, whereas in the past with the monolith, you're much more tending to be over in the world of standardization. With the microservices and finer grained architectures, you get a bit more freedom. So in terms of where to standardize, it's probably worth talking about some traditionally used metaphors in terms of system design. So how many people here would consider themselves an architect? Or at least called an architect? Thank you, Jim. So many people, probably about last 5 years ago, more people would have put their hand up. I think now people get the sense that an architect is a little bit of a dirty word.
Most sexy.
Yes, thank you, Jim. If you think about where the word architect comes from, it's actually a reassuring metaphor for all of us, right? Because if you think in this place here, we're in a big building, it was designed by an architect, and unlike most of our software, it's not falling down right now, right? So this makes us feel good. We think about how an architect works, and putting aside the sense of artistic beauty that most good architects should embody, not all of them, seeing some of the buildings around Brisbane, but nonetheless, they should embody. But the way they work is they think detail about the problem. They spend a lot of time coming up with very, very detailed plans. They then give those plans to a builder and tell the builder what to make. And in the past, that's exactly how we approach IT and building systems. We have somebody over here who comes up with a plan and then tells these people over here what to do and implement. The problem is that software is not like architecture, and the software we create are not like buildings. We create software for a significantly more changing environment than architects create buildings for. Probably a better metaphor is one that I borrow from one of my colleagues, Eric Dernenberg, and he talks about the concept of sort of system design and architecture is that of town planning. So how many people here have played SimCity? That's good, yeah. Not this version of SimCity, which is a borrowed thing, but I remember SimCity 2. Oh, SimCity 3, I think it was where you had to connect sewage pipes up. That was a bit of a pain. But nonetheless, in SimCity, what you did was you create zones. Just like a town plan, you say, over here, we're going to have a commercial zone, and over here, we're going to have an industrial zone, we're going to have a residential zone here. We want the residential zone near the commercial zone so people can get to work and go shopping, but we don't want, say, the school next to the sewerage plant. You didn't worry overly about what exact buildings grew up in those zones. What you did was you created those structures and you placed those zones, and you gave a great deal of care about how those zones were connected. The roads, the electricity, that was important, not the exact buildings. That's actually a great metaphor if we think about software. The idea being that as an architect, our job is effectively to define the zones and give people autonomy within those zones, but give a great deal of thought to what happens between those zones. So if you think about a service, the areas that we want to standardize on are our interfaces. How do our one service talk to another? Because getting that stuff wrong actually has a high cost. How do we know how that service is behaving? We want to be consistent in our view of that. And also, how do we deploy our services? We don't want to deploy them all in a very different way. But just like a town planner doesn't tell me exactly what buildings to build, there are at least something called building regulations that make sure that if one architect does screw up, a building doesn't collapse and kill everybody. There are things that we have to do to make sure our buildings are safe so we don't endanger the city. The city is a living, breathing object, the software as a living, breathing entity as well. So we also need to think about the concept of architectural safety. So if you want to think about our system design in terms of town planning and town architecture, what we're going to think about is sort of within the zone, you want to let those boxes, those services, sort of define most of the things they want to do themselves. So you want to give teams maybe that own those, say inside the box you do what you want. But between those services, what you really want to do is a bit more, that's where you need to think about the standardization a bit more. That's where you need to get more upfront thought. How do these things connect? What are my roads, what are my electricity like? So this is the first tip. Standardize in the gaps between the services, but be very flexible about what happens inside the boxes. Let's think about interfaces. So here's my service. I've got some internal representations. These are functions, data structures, whatever they might be. Now if I expose those over the wire and my consumers grab hold of those internal representations, I have a problem. I now find it very hard to change as a service because my consumers are bound to me. I now can't change and evolve how I want to. I'm coupled. And coupling is very, very bad. We want to avoid coupling at all costs. This is a slide I stole from Scott Shaw, which sort of talks about different integration styles. We start over here on the far left with the integration style that keeps ThoughtWorks in money, which is data-oriented integration. This is the traditional multiple services integrating on one database or database-to-database integration. Very tightly coupled approach to the world. I remember one client back in 2007, we couldn't find out how many services were actually integrated in one database, so we turned it off during the day and waited for the phone calls. We found 40 separate applications that were integrating on our database that day. That was a fun Friday. And then we sort of have procedure-oriented integration. Here, think the method call within a process that you now decide to put across a process boundary. The problems with these sorts of integration mechanisms are that they're often quite closed and quite brittle. Think of a standard create user method that you might have, which takes first name and last name, and then suddenly you want to change that method call to now just take full name, because many parts of the world you don't have first name and last name. If that's across a process boundary, I've now got a second method call to add. It becomes quite a large sort of endpoint space, and it's also quite a brittle calling. The thing is, it's very easy to do. Serializing our objects is very easy. .NET makes this trivially easy, Java makes this very, very easy. RMI is actually pretty easy to do. It's also terrible because we end up with very, very coupled systems. Better than database-oriented integration, but still not great. We've then got document-oriented, where you think about the forms that flow around our organization between different departments. So thinking here about documents that we send around our systems, maybe XML or JSON documents, and services pull out the bits they need to. This is an approach actually commonly used when you do things like event-driven systems, actually. You're in a better world here. You're significantly less loosely coupled. And then we have the resource-oriented world, where services don't actually expose their resources, they just give you representations based on what's asked for. And if you're doing something like using, say, REST over HTTP, you even get to take advantage of things in the HTTP specification. So rather than create user, delete user, update user, I just have user endpoint, and I can use the HTTP verbs that have well-defined semantics as to how they behave. And from our experience, the further you move towards the right, the significantly less coupled your systems are. And so this is a really good thing to get your head around. I'm not going to go into it in detail, but if you look at REST in practice, that gives you a good idea about the different types of REST and some of the advantages you can get from that world. So avoid RPC mechanisms and avoid shared serialization to decrease that coupling. You may actually have legitimate reasons for different types of integration. And it's probably a good idea to standardize on one. Say, for all, our default choice in integration is going to be, say, REST over HTTP. But for asynchronous communication, we're going to pick XML over JMS, and maybe when we have real low latency requirements, we might pick, say, a proprietary browser sockets implementation. Like 3 different conventions for integration in very specific use cases is a good idea. 20 is a bad idea, and I have seen 20. You do not want to have 20 different ways of talking to each other. Pick 1 or 2 or 3 that make sense and try and stick to them, otherwise your world's going to become like spaghetti. All these integration techniques I spoke about, there were some things that are built into the standards and the underlying specifications, but they're still quite open. For example, how do I do error handling? Yes, I might understand the 400 or the 500, but where's the error message in my payload going to come from? Should I be using verbs or nouns? Should I be pluralizing? How am I going to do pagination conventions? Apogee do some products which I do not like, but they do a very good freely available book called Web API Design. This is actually just it takes conventions from lots of different publicly available APIs, like the Twitter, the LinkedIn API. There's bits in it I don't like because it is really focused on consumption of public APIs, but there's some really good common sense advice in here. And so for many teams, we download this book and we go through it, redline the stuff we don't like and take the bulk of it. Just having some sensible conventions that say things like, when I give you an error and you get an error response back, here's where you can look in the payload to find the information that's going to be useful to you. This doesn't talk enough about some of the stuff in REST, so I would also suggest taking that in conjunction with REST in practice. But come up with some sensible conventions and stick to them. And if you can just take a book like Web API Design and cross some sections out, that's a pretty good starting point for you. So I'd definitely start there. Another integration problem. In the old world with the monolith, we had our transactions and our transactional boundaries. Transactions with databases are a very good thing, they're a nice thing to do, but they can be dangerous when we integrate our systems and services. So here I have my payment service talking to my inventory service. My payment service said, look, I want you, inventory service, to take an item out of stock, but don't really commit it right now until my payment goes through. And if my payment doesn't go through, I'm going to wind that transaction back. This is the thing that often happens when we move towards these sort of integrated, so we move away from the monolith into these finer grained systems, and we start talking about the distributed transaction. Now, I don't have enough time to explain why this is a bad idea, other than to say this is about distributed locking and cap theory. So don't do this because cap theorem, basically. Please don't do this. Avoid distributed transactions at all cost. Try and subdivide your problem. Try and embrace eventual consistency where you can. Move towards a place where you make as small an area of your domain as possible where you have to have distributed transaction integrity, and then consider making those two things one service again if you have to. Do some reading on this stuff. It's very important to get right, but distributed transactions are going to kick you in the behind. So don't do them. Monitoring. So when we had the big box, we could get very lazy about things. When there's something slow and a user comes to us and he starts complaining, what's the problem? Well, it's that guy. I'm getting an error. What's erroring? That guy. I can smell something burning. What's that burning smell? It's that guy in the corner, right? So from a monitoring and a response point of view, we can be very, very lazy. And it's just a thing in fire in the corner, because that's always a thing on fire, and it's always going to be that guy. We have a more fine-grained system, though, and we have an unhappy user that comes to us, and they're saying something's not working. What's not working now? The world's a bit more of a nuanced place. You are going to have to get much better at monitoring with a finer-grained architecture. If you don't spend any time on monitoring and alerting and problem identification, and you've gone to a fine-grained architecture, you're going to be in a world of hurt and reliving a red wedding. So here we are with my fine-grained architecture, and let's imagine I've gone from the single box, and before, when I want to go and get a log file, I would log into that machine and look at that log file, and the world is good. And now I go to 2 or 3 or 4 machines. I need to get the log file, see what's going on. What's the first thing I do? I open up lots of xterms, right? That's what I do. Right? I get lots of monitors, pretend I'm a stockbroker or in the matrix or something, and I get like 15 xterms, I'm running tel-f and running greps and all of them. And then I discover SSH multiplexing, where I can run the same grep in 15 separate terminals. And it's all great, fantastic, and I feel so cool and Uber. Stop doing that. This is the 21st century. You need to grow up, right? You're not a badass if you use an SSH multiplexer. Instead, there are only about 50 tools that will solve this problem for you. And what we're talking about here are log aggregation tools. So you want to be getting the log files from your services onto a central location where you can actually dive into those logs and see what's going on. If you have lots of money, go and buy Splunk, because Splunk is awesome. Most of the people I talk to don't have Splunk money, but if you do, just go buy their product and you'll be very, very happy. It plays very well in this space. Traditionally, logs are a passive tool. When something goes wrong, we use the logs to actually find out what happened and why. When you start aggregating your logs together, tools like Splunk can actually help you understand what's happening and alert you based on what the logs are seeing. It goes from being a passive tool to an active tool. If you want to start off yourself and you just want some open source tooling, Logstash is very good in this space. Logstash is a daemon that runs on the box, collects those logs. It can even restructure those logs for you to normalize, say, log formats from multiple different sources. And it then supports multiple destinations, including Kibana, which is actually a front end based on Elasticsearch. This gives you some of the basic features in Splunk, the ability to search those logs, run queries, and even pull stats out. Getting a setup of this sort of nature wouldn't take you more than a couple of days, and you will thank me for it. And you have one place to see all of your logs. You should also be monitoring response times, at the very least, everywhere. In fact, you want to be grabbing metrics from every single one of your servers and aggregating them centrally. But start at least with response time. If something is slow, you'll find out it's slow at the entry point to your system. So then you say, okay, well, looking at it, it's normally a 2-second response time. It's now a 4-second response time. What if my other services are seeing a spike in their response times? And then you can trace it all the way through. Putting that data into something like Graphite is actually fairly easy. If you're storing this in something like Apache log format, then Logstash can actually put this information right in Graphite, which is a great time series store for metrics. It's a fantastic system. And that will help you isolate the problem. Graphite can actually even pull information, it's actually designed for pulling information from things like our CPU, your memories as well. NS Client++ for Windows, CollectD for Linux will get all of your operating system level stats into Graphite. I've done this for a few clients. We can normally get this set up in half a day. If you're pulling information as well from your application level monitoring and your sort of basic system performance and your operating system level performance, and you're pulling this into one place, and you can actually see correlation across all of that, and correlation over time, you're going to be significantly more aware of what good behavior looks like, and it's going to be much easier for you to identify bottlenecks in your system. So grab that stuff and aggregate it. You may actually even want to put a display on each node. This is something I do in actually all my projects. Every single node, I can actually see this information in a human-readable form. This is actually an example of a web page that was on a hidden URL for every one of our services. In this system, this was actually the source of data that other systems were using for aggregation. This was both human-readable and machine-readable HTML files, using micro formats, basically. So So it shows me how many 400s, how many 500s. This stuff is very useful because it also gets developers in the idea of thinking about their applications having to always expose this information. It can be used for running tests and just get a better understanding about how those nodes are behaving. So capture metrics and logs for each node and aggregate them to get the rolled up picture. You have to do this, otherwise you're going to be in a world of pain. Some of these systems can become quite complicated. They often have sort of semi-emergent behavior after a while. And that can be hard to track down when you get sort of odd errors. There's a few things that you can do actually to help alleviate this. One technique I've used a few times that is very useful is this idea of the synthetic transaction. So rather than just looking at, say, CPU and response time, what I actually want to see is my system working how my user wants it to work? So at a trading company, we were doing these credit derivative pricing. So this is basically you get an event comes in and you trigger a pricing event and you want those responses back in a very short period of time. So what we actually did was every minute we sent a real trade through the system that just ended up in a book that no one looked at. So it didn't have any destructive behavior. And Nagios actually triggered that trade off, and if it didn't see a response on the pricing update for that field, within 2 seconds it would alert. We found that that synthetic transaction was significantly more effective at identifying problems than actually all of our other monitoring. And if you have functional tests right now for your system, you have the beginning of what can be your synthetic transactions. Take some of them, take the ones that aren't destructive or make them non-destructive and just run them periodically in your system to get a real sense of are things working. Another great technique for identifying some of the problems you're going to experience where you get these weird outlying errors, you'll often get like weird things like packet storms happening or an odd stack trace that occurs through a sequence of events you can never quite unpick. How the heck did that happen? If you get a cascade of calls at maybe 20 or 30 deep, unwinding that and tracking it back to an originating request is challenging. The one thing you can do to help you follow this trace and to identify that nasty error is to actually use something called a correlation ID. So when the initiating request comes in, effectively generate an ID and associate it with the request and pass it all the way through. And have subsequent calls also take that correlation ID through as well. If you're then logging all of your calls as they go through, you should put the correlation ID in your logs. And you could then use something like Kibana to actually go back and say, what are all the logs I've got for this correlation ID, and let's track it back. You can even get more advanced and actually use that to create diagrams of the flow and how things happened, assuming you've got synchronization on your times. Obviously, correlation IDs require a convention to be used across your organization, but they're a very good idea, and they're something you might want to consider putting in up front to help you catch these problems before they happen. So use correlation IDs to avoid to help you track down nasty bugs. Now into the complex world of deployments. Some of the reasons that we move towards finer-grained architectures are often to allow us to experiment with different technology stacks and to embrace new things. But this can become problematic when it comes to actually shipping the things and getting the things deployed into production. Mostly because, okay, I'm going to target one component for deployment, and here I am, I'm deploying that, and I have to use, I don't know, one tool chain because it's a Node application. And then over here I'm using a different tool chain because it's a Go app. Or over here I've got to use a different tool chain again because this is my JVM application. And this becomes a bit of a pain. Most organizations I know that move towards finer-grained architectures come up with some mechanism for actually abstracting out some of the underlying differences in the platforms they're deploying. In fact, the more you can abstract out the underlying differences in the technology stacks, the more freedom you're going to give people to try out new things. You lower the barrier to entry. If you have that abstraction point, yeah, sure, you can try Go out, because all we'll do is we'll just implement something in our deployment abstraction to make that possible. So a tool I use actually quite a lot for this is something like Fabric. So Fabric is a Python program that lets you actually dispatch command line. It makes it very easy for you to write command line programs that are called Python functions. It comes with support for things like SSH and just running commands locally or remote machines. So I can very quickly create things like a command line, say fab, which is a Fabric entry point, deploy, which will call a function called deploy that can go do stuff. And so then I have the full power of a programming language to create abstractions that under one hood might go and call npm, on the other hood's calling bundler, or is just copying a file around for something like Go. Obviously, you can do things like this with Capistrano. You would want to avoid JVM-based tools here because the spin-up time is just too slow. How many of you here do continuous delivery? Okay, it's a few, right? So continuous delivery being the idea that every check-in is a release candidate. And so we have things like the build pipeline. The build pipeline is here for us to verify whether or not the piece of software we just checked in is ready enough to go into production. So as it goes through, as that same version of the code moves through, we give it like badges. Yes, you're good enough to go into production. Yes, you're still good enough to go in production. And so we get more confidence as we move through that pipeline. But we're often tuning it so we get faster feedback early in that life cycle because we want to be able to react quickly. So as a result, we often want to move our artifact through different environments because often the cost of standing up a production-like environment is quite expensive or it takes a long time. So we tend to get into more production-like environments as we move closer towards production. And as we're more towards development, our environments are maybe based around fast turnaround. So maybe I'm only deploying locally, then maybe my CI service is running those things locally as well. And then maybe when I get out to, say, a performance environment, I'm standing up a whole Amazon environment that mimics my production environment, but it maybe makes 25 minutes to spin up. So those environments are also sort of different as we move through. But we don't want to have different ways of deploying our system for the different environments either. We don't want to have a different deployment mechanism because what we want to be able to do is say, well, the software we deployed in QA, we're fairly sure if we run that same deployment process, it's going to work in production as well. We don't want to introduce new nuances further down that pipeline. So you take something like Fabric, you can just introduce the concept of the environment. So rather than now just fab deploy, so the colon is how you pass arguments into the function, I could pass in an environment identifier. And at quite a few companies, what we've done is then effectively model the environment in something like a YAML file or something. So I have the ability to deploy locally, I have the ability to deploy on Amazon, I have the ability to deploy on LXC, implemented effectively as a set of Python functions, and they're parameterized by, say, YAML files. So here I've got a YAML file on the left here, but actually the whole load of information is my prod environment, and it's got information about Amazon AMIs. So if I say prod, it pulls up that YAML file, runs it into my Python Fabric functions, which uses, say, Botto, which is the Python Amazon API. Now, we got to this over a series of weeks of building these abstractions out. But what you end up with is a unified command line. I say deploy, the two things that change are maybe the version I want to deploy and the environment I want to deploy. I want to create a new environment, I create a new YAML file. We got this thing working for LXC and local environments and even for Amazon. So have a single way of deploying services in any given environment and build out those abstractions to allow you to support new underlying platforms. This is actually the space. If you're worried about lock-in to, say, a cloud vendor, this is how you avoid a lot of that. If you create those abstraction layers for you, that goes away to a great extent. If you're monitoring in a generic way, with your hooks and you're deploying with an abstraction layer, if you want to, say, try out a new cloud provider, you want to try out Rackspace, then you just go and implement an abstraction that works on Rackspace. And your build pipeline calls don't really change. And from the outside world, you shouldn't notice any difference. And so you effectively, you hide in one place where the differences between your environments can be. So you think about the example of the build pipeline. So here's my customer service, and I'm moving it through the pipeline. It's a new version, and I'm giving it lots of tick marks. Very happy with this. I feel good about this. Now I can deploy it into production, right? Well, maybe, maybe not. Because in production, I've got my finance system talking to my customer service, right? So what I actually also want to verify is not only does the customer service work in isolation, but does my customer service work, does the new version of my customer service work with the version of the finance system that's in production? Now, one option to solve this is to do something like an integration test. So, at the end of the pipeline for the customer service, I take it together and I get the production version of the finance system, and I run them together and say, do these things work well together? Now that's okay, but integration tests have some challenges. If you've got lots of services They can take a while to actually run. They can be quite brittle. You're more vulnerable to sort of false negatives from environmental problems. They can also have poor isolation. So almost by definition, if an integration test fails, it's part of a large amount of scope that could be to blame. So maybe you want to do some integration tests, but you actually want to keep it to a minimum if you at all can. So is there a way actually to find out, am I going to break the finance system without having to run an integration test? So if we think about service design, right, at some point, hopefully, the people involved with building the customer service had a conversation with the people building the finance service and said, well, what stuff do you need, finance service? And the finance service says, well, I need to make these sorts of calls. These are the kinds of things I need to be able to access. So, okay, great. And then the customer service team went off and wrote that API. And then the finance team called it. Now, what if that conversation actually resulted in effectively a codification of that conversation? So what if, as a result of that conversation, the finance team actually wrote a test explaining what their expectations were of how the customer service was going to behave? And then the customer service team ran that as part of their pipeline. This is a concept called consumer-driven contracts. So in this world, the finance team says, okay, so that's great, and here's our understanding of how you're going to behave. And maybe they actually paired together to write those tests. And it's up to the customer service to expose fixtures to make that possible. But then every single time the customer service pipeline runs, you run those tests in isolation, and if you break them, you get to either say, that's a problem, I need to sort that out myself, or actually I need to go have a chat to the finance team and say, we're going to introduce a breaking change, how should we manage rolling that out? So use consumer-driven tests to catch breaking changes early. There are other challenges though, especially when we think about deployment and build pipelines when we have multiple services. Especially when we have a path to production that takes a while. So here I am, I've created some new version of my code, it's run the gauntlet of my build pipeline, and it's production ready, but sort of sits in a pending state, probably because I've got some other activities that have to happen afterwards. Maybe there's a manual go, no-go decision. Maybe there's a once-monthly release window that I've got. And so while my code is sitting around, production ready but not yet released, maturing like a fine cheese or getting moldy like a piece of bread, depending on your viewpoints, other changes also build up. So other services put their changes through as well. And I end up with a growing pile of stuff, a steaming pile of stuff, ready to go into production. And now we sort of have a problem, because now all of that stuff is going to have to hit production at the same sort of time, because if I've done any integration testing, I sort of only know that that whole bundle works together at this point. Now there are problems with a big release. No sniggering, Jim. When you have a big release, you have a lot of risk. Problems are more likely to occur. When something's risky, people actually, certainly in this environment, tend to want to do things less. If a problem occurs during the deployment, then people are more likely going to want to put more hoops you've got to jump through back into the process, which means your releases are taking longer. If your releases take longer, they grow up. They get bigger and bigger and bigger, which increases the risk, and well, this is a vicious circle. This is a very bad place to be in. Do not let your changes build up. Release as soon as possible, and you want to release if ideally one service at a time. In fact, I would go as far to say as if you've got 4 services right now, and you have this problem already with 4 services, that you end up always seeming to have to release 2 or 3 or 4 of them together, then fix that problem before you add a 5th or a 6th or a 7th service. Releasing multiple fine-grained services, and the fact that you always have to release them together, is way worse than probably having a monolithic application, in my opinion, especially if what you're trying to optimize for is throughput and getting things out on time. So you really need to work hard to resolve this. This is often down to looking at your testing practices, solving your integration challenges, but really this is something to really strive for. Finally, let's talk about architectural safety. So here's my system. Let's imagine I've got my call coming in at the top right here. What happens if that link goes down there? Maybe a rabbit gnaws through some Ethernet cable. It has happened to me, believe it or not, and we know it was a rabbit because we found his electrocuted corpse next to it, because it then went and ate some electric cable too. But if you built systems how I did back in 2007, here's what would happen to your system. Well, that would die, and then that would die, and then that would die, and then the whole thing would fall over. You know, the classic cascading failure. Cascading failures kind of hurt. System I was involved with, we were throttling a legacy application, so we were effectively proxying calls. We'd moved away most of the behavior. There's maybe 5% or less of our functionality and significant less of our revenue was coming from this downstream service. And one day it started acting slow, and just slow. So our connection pool that was talking to it started timing out, and that was kind of okay, but we didn't have timeouts on the things waiting for things from the pool, because at that point HTTP client didn't give you a default timeout, and we didn't think to configure one. We went from 30 concurrent connections to 800 in the space of about 2 minutes, and our whole system fell over. So at that point, I cursed myself and then went and read Release It, like everybody should. This is Mike Nygaard's book, which talks a lot about architectural safety patterns. Effectively, this is born through bitter experience of having to help systems scale and handle failure well. So use timeout, circuit breakers, and bulkheads to give you that architectural safety to avoid things like cascading failures. And these are things you probably want to be very firm on. So in our example, we had our timeouts misconfigured, and what we actually did was move towards a system where we had a full-on circuit breaker. So just like in your house where you get an electricity surge and a circuit breaker pops, it avoids frying all components. And if you want to go rewire your house, you can manually flick a circuit breaker and go and rewire the house without being electrocuted. So in systems, a circuit breaker is something where, okay, my downstream service is unhealthy, I'm actually not going to send any more requests, so effectively I'm going to blow the circuit breaker and give that service time to recover. I can then understand how to degrade the behavior of my application. So maybe I turn off some functionality, or maybe I fail fast, but I certainly don't pass that failure back up the chain. And the bulkhead is the idea that your downstream pools are actually separate connection pools, so that if one has problems, the rest are left alone. These used to be tricky to implement, but there's now some good open source implementations of that, which I'll mention in a moment. So read this book and put these things in, especially for downstream failures, otherwise you're going to have pain like I did. So we talked a lot about the standardization, and a lot of this is about freeing up our people to concentrate on the bit that's most important to them, which is maybe implementing the logic that makes this service special from the rest. We want to avoid the need to do the same thing over and over again. A lot of these tips I've outlined become conventions in your own organization. That's a lot for a developer to hold in their head. So wouldn't it be great if we can actually find a way for them to not have to worry too much about what the conventions are that enable us to have these fine-grained architectures, but it can instead concentrate on the problem at hand. So they have a place where their business logic goes. They have maybe out of the box a halfway sensible API for handling REST APIs, maybe some downstream support for other services, and even a place where my metrics can be stored so I can send those to other places. This is actually much easier than it used to be. If you're on the JVM, grabbing something like Drop Wizard gives you a lot of this out of the box, especially if you combine it with something like Hystrix, which is the Netflix circuit breaker API. This idea of service templates, effectively codifying these conventions for your organization, are a great way of making it easy to do the right thing. And do it as a team and do it collaboratively, but do it for, say, each of the deployment platforms that you're going to support. Maybe don't stop people using a different language or a different platform, but say, that's okay, but you're going to have to go implement those conventions yourself. But if you use one of these 4 stacks we've already got available for you, that's good. Make this internal open source. We use it as quite a few clients. It's a great way to codify this stuff. I've talked about a load of stuff here. If there were 2 rules that I'd like you to take away, it's this one. First, standardize in the gaps. Be flexible about what happens inside the boxes. And secondly, this one. Release services one at a time if at all possible. And if you can't right now, fix that first before you go any more fine-grained. I've got 2 other talks that sort of touch on some of the more generic ideas around this. One about how you architect to make it easier to release more frequently. One about how you split services up. You can go and find the videos on Lanyard if you're interested. But other than that, thank you very much for your time.